All right, so Mac 132, Blueprint Reading 2. Today is the 18th of February. What did we learn today? Well, I handed back the retest and got a little bit better picture of what is and what isn't syncing in basic GD&T. And what I determined was we aren't understanding what a datum feature is. A datum feature means what is serving as the datum on this part. Which feature of the part is serving as the datum? So we had to think about that for a while. We went over naming all the different features you might find on a part, like slots, grooves, holes, edges, burrs, anything that enables us to get control over the model. We give features names like boss and slot and things like that so that we can understand them and that we get power over the blueprint. Well, the same thing kind of goes with datum features. We have to understand the features that make up the datum so that we can get control of the GD&T and the tolerancing that goes along with it. So what we said was, if you can see that a dimension has a datum call out attached to it, and there are dimensions there, then it is going to be an axial or center line type of datum feature. If it's like flatness attached just to a surface and there is no dimensioning or any other call out onto it, then it is just a surface datum. That surface of the part is going to serve as the datum for your measurements. So this has profound effects on how you measure things, and I went over that about the example of a pin sticking down into a hole, and you measuring the perpendicularity of that pin. You're not measuring the surface of the side of the hole. You're measuring the axis, the perpendicularity of the axis of that hole, because the pin fits all the way down into it. All right, so then we moved into tolerance zones, which is kind of related right to that. What is the shape of the tolerance zone? We had like this edge right here. If this were straightness, the tolerance zone would be two parallel lines, let's say 5 thousandths thick, apart from the line of the thing. And our part to be good would have to lie in that zone that is drawn or created around that straight line edge. Position is a good deal easier. The position of a hole located at the center of this perfect location right here has got a circular tolerance zone around it of, say, 8 thousandths. That means we can be 4 thousandths off in any direction from the exact center of where that hole, the axis was, and still be good. So the tolerance zone in that case is of a circular shape. You have to look at the GD&T for a long time and think about what it means in practical terms, not only for the shape of the tolerance zone, but what it's going to mean for how you machine it in the shop. Which machines are you going to pick? Do you have to have a surface grinder to do this, or will a milling machine do? Am I going to be able to repeat these parts enough, or am I going to have to use a CNC machine? So that is the shape of the tolerance zone. The other thing that didn't seem to be sinking in that good was worst case scenarios for like wall thickness. If the part was giving you plus or minus 10 on the overall length, and you are -5 or minus 10 thousandths on it, then what happens to the wall thickness? And then you got to combine that with the tolerance zone that I just described up over here to get a final wall thickness where the part will still be good. So we got to understand worst case scenarios. Again, that has everything to do with your machining decisions and how you're going to make the part. And if you go in with this knowledge ahead of time, then you can breathe easier when you're out there in the shop. After you've made a tiny little error, you know it's still going to be plenty good for the wall thickness. But if you don't do that thinking ahead of time, you go out there in the shop and you say, oh my goodness, I'm off this far, then you have a lot of work to do to make sure that your part is still good. Last thing was we talked about runout and how runout and concentricity and circularity are all kind of related together. But runout is a cheap thing to check. We talked about the difference between circular runout and total runout, and went over that. Circular runout is in one place. Total runout is over the entire length of the shaft and the surfaces and the axis that they're tied to. This is an axis. When you see runout attached to a datum reference, or a datum, not a datum reference, a datum tied to a runout feature control frame, that means that the center line axis of the part is the true datum feature. All right, we did an exercise in class where I handed out more NIMS prints that had lots of GD&T on them. Thank you for your participation in that. I think we did some active learning answering these questions. This is from the grinder block print. What were the overall dimensions? How much can I deburr an edge before I scrap the part? And I went over how if we have to harden and leave stock on the part before we finish it on a grinder, we've got to allow for that deburred edge. Then the limits of thickness. This was a tolerancing question. Look at the maximum and minimum limits of thickness. Describe the angularity tolerance zone as two parallel lines along a 45-degree angle that are 3/1000ths apart, equally spaced about the line. Datum C was an axial feature. Datum A was a surface feature. The minimum wall thickness, we came out to be this, and it was interesting enough that we had to round the 4th decimal place up to allow for our figures when we divided by 2. So I want to see this interpreting that feature control frame above datum B, and then what kind of practical considerations that might call for out in the shop. Thank you, and we will see you next week.